Alcohols can also undergo elimination reaction, in which case it's going to eliminate water, and therefore it's called as dehydration reaction. Normally, this reaction is catalyzed by acid. Now, why you have to use acid? Again, for the same reason that because alcohols do not have a good leaving group, it has to be converted into a good leaving group with the use of the acid. And this reaction requires huge amount of heat, and only then you will be getting the product, which is an alkene. Dehydration is normally a reversible reaction. And if you want to make the reaction go in the forward direction, then you have to eliminate water. You have to constantly withdraw the water that's being formed. And then you can increase the products. When you dehydrate a secondary or a tertiary alcohols, it's going to go through the E1 reaction. Let's look into the mechanism for this reaction. The first case, the hydroxy group is actually going to be protonated, which is going to be converted into a good leaving group. Let's draw the structure for that part. So remember, the oxygen with its lone pair of electrons, it's going to go grab this hydrogen, and it's going to thrust these electrons onto oxygen. Thereby, it's converted into a good leaving group. Now, in an E1 reaction, we know that a stable carbocation is formed, right? Now, the leaving group is going to leave, and it's going to be forming a stable carbocation. And here is your carbocation. And in the next step, we need to look into the beta hydrogens, right? The abstraction of the beta hydrogen by the base happens, thereby forming the double bond. So here, since water has been eliminated, that's going to act as a base. And we already know that there are two hydrogens in here and two hydrogens on here, because this is your beta carbon and this is your alpha carbon, right? One of these hydrogens will be abstracted, okay, thereby putting the double bond here. So the product here is going to be an alkene, cycloalkene. Dehydration is a regioselective reaction. Any elimination is a regioselective reaction, right? So again, the same thing is going to happen. There, in the previous example, we had formed only one product, but in some alcohols, there is a possibility that it could give more than one products, out of which one product is going to be formed in major quantity. And such reactions is called as regioselective reaction. Now let's look into the mechanism for this reaction and what are the products that are formed in this reaction. The first step, the hydroxyl group with its lone pair of electrons is going to go grab the hydrogen from the acid molecule, right? And the electrons are going to be thrusted onto oxygen, and in which case it's going to form a good leaving group on this alcohol. Since we are talking about the E1 reaction, the first step is going to be the formation of the carbocation. And here is your carbocation that's formed. Now this is a tertiary carbocation. Now in order to identify all the products that are obtained, you need to identify where is the alpha carbon and also the beta carbon and abstract the beta hydrogen and form the products. So here is your alpha carbon and here are your beta carbons. And you need to abstract one of these hydrogens here or one of these hydrogens from here. Let's find out what are the products that you're going to get if we abstract this hydrogen first. If I'm going to abstract this hydrogen, it is going to result in this product. And if I'm going to abstract this hydrogen, then it's going to result in this product. And between these two, which one is the major product? We already know that this is going to be our major product. Why? Because this is more substituted. And according to Zaitsev rule, the more substituted alkene is the one that's going to be formed more because of its stability. Okay, now let's look into the second reaction. Here again, the first step is exactly the same. The electrons from the oxygen is going to go abstract this hydrogen, right? And it's going to, the electrons between the hydrogen and the oxygen is going to get thrusted upon oxygen, and it's going to form a tertiary, a compound with a good leaving group. And in an E1 reaction, the leaving group is going to leave, resulting in the formation of the carbocation. And here is your carbocation. Now, if you closely look into this, there are 3 different beta hydrogens on this. Let's locate those. So here is your beta carbon, here is your beta carbon, and here is your beta carbon. And we already know that this carbon has 2 hydrogens and this also has 2 hydrogens. Whether you abstract a hydrogen here or here, it's going to result in exactly the same compound, right? So let's draw the product that you will be getting if you abstract this hydrogen. This is the product form. If we abstract this hydrogen, or this hydrogen. Okay, and you can also abstract this hydrogen. That's going to result in a different product, which is going to look like this. So now between these 2 products, which one is going to be the major product? Right? Obviously, it is going to be this one, again, exactly for the same reason, because this is more stable, because it's highly substituted according to Zaitsev rule. Tertiary alcohols are the easiest to dehydrate. If you want to look into the rates of the reactivity of the different alcohols, the tertiary alcohols are the easiest to dehydrate. That is because it has the ability to form the carbocation very easily. So the order of reactivity is going to fall in this order. The tertiary is going to be more easier to dehydrate, and then comes the secondary, and then comes the primary. So keep in mind that a tertiary alcohol and a secondary alcohol will go through the E1 mechanism, whereas the primary alcohol is going to go through the E2 mechanism for the elimination. Okay, and also keep in mind that in an E1 reaction, wherever carbocation is formed, you need to also look for the carbocation rearrangements. E1 reaction, obviously you're going to form the carbocations, so always look for the carbocation rearrangements. Here is one reaction where it can result in the rearrangement of the carbocations. Now let's look into the first step. The first step is going to be the alcohol is going to be converted into a good leaving group. So with this, it's actually going to get and the leaving group leaves and it's going to form this carbocation, right? And in the next step, a methyl shift, 1,2 methyl shift happens. Do we have a methyl group in an adjacent position? Yes, we do have a methyl group. And we know that this is a secondary carbocation, which can be converted into a tertiary carbocation, provided this methyl group is going to make a 1,2 shift. This methyl group has the possibility to do a 1,2 hydride shift. So the product here is going to be it's going to look like this. The other carbocation is going to be a tertiary carbocation. Now that we have formed a stable tertiary carbocation, your next step is going to be abstraction of the hydrogen by a base. So the base comes in and abstract the beta hydrogen. Now where is the beta hydrogen? So remember, this is your alpha carbon, this is your first beta carbon, and this is your second beta carbon. And these 2 beta carbons are one and the same. These 2 beta carbons are one and the same, so whether you abstract the hydrogen from here or here, it's going to result in exactly the same product. Now let's find out the products here. If I'm going to abstract a hydrogen from here, then it's going to result in this product. And if I abstract the hydrogen from this carbon, then it's going to result in this as the product. In between these two products, we already know that this is going to be our stable product because of Zaitsev rule. Stable product because highly substituted, or this is going to be our major product, highly substituted. Of a primary alcohol is actually going to be an E2 reaction. But in this case, you get two different products. One is your E2 product, and along with that, you'll also get the SN2 product. Okay, so it's going to be actually a mixture of two products. Now let's look into the mechanism. The first step here again is the activation of the alcohol to convert this strongly basic OH group into a weak base, thereby converting into a good leaving group. Okay, so where this oxygen, lone pair of oxygen, is going to abstract this hydrogen and it's going to thrust the electrons onto oxygen. Let's write down the product here. Now it's been converted into a good leaving group. Now in this case, there are two reactions that are possible, E2 or SN2. Let's write on the E2 product first. If it's going to be E2, remember you have this hydrogen here. The base is going to go grab this hydrogen, thrust these electrons onto forming a double bond between carbon, and the leaving group is going to leave, right? So the product would be an alkene. And the water is also going to get eliminated. If it's going to be a substitution reaction, the product is actually going to be a protonated ether first, and then finally it forms the ether. Let's look into the mechanism for that. If it's going to undergo the substitution reaction, another molecule of ethanol is going to act as a nucleophile. So let's have this ethanol here. And it's going to act as a nucleophile, attacking this carbon through the backside effect, and it's going to thrust these electrons onto oxygen, so the water could be a leaving group. Okay, let's write down the product here. The product here is actually going to be a protonated ether, which is going to look like this. Remember, this oxygen is trying to form a bond with this carbon. Already it has two bonds, one with hydrogen and one with this carbon. Now it has totally three bonds, and therefore it should have a positive charge. Now the base, so in this reaction, water is going to be eliminated, right? And that's going to act as a base to grab this hydrogen. And it's going to neutralize your oxygen, finally giving the product, which is your ether. Okay, so when a primary alcohol undergoes dehydration, it will result in both E2 and as well as SN2 products. Remember, an E2 reaction is a regioselective reaction, wherein if there are a possibility to form more than one product is going to be formed in major quantity. So here is an example for it. Here is an alcohol. What's the first step when it's going to react with an acid under heat? Obviously, it's going to get activated, right? Let's write down the activated product, activated alcohol. So here is your activated alcohol with a good leaving group. Now, since this is an E2 reaction, what's the next step? The beta hydrogen will be abstracted, right? So I'm going to show the beta hydrogen here. In the presence of a base, this beta hydrogen will be abstracted, and it's going to form the double bond between these two carbons, and the leaving group is going to leave. Okay, let's write down the product. Here in this case, the product is actually 1-butene. But there is something interesting happens here. Because it's an alkene, we know that the alkenes would undergo electrophilic addition reaction in the presence of acid. We already use huge excess of acid here. So that acid is actually going to react with this double bond, undergoing an electrophilic addition reaction. And we already know that the electrophile is going to get added to the carbon, which has the most number of hydrogens. So this is the carbon that's going to take the electrophile, and this carbon is going to be your carbocation. So let's write down the product. So once the H plus has been added, this is going to be a product, right? And now your base is actually going to go grab the beta hydrogen. Let's find out what is the alpha hydrogen. Here is your alpha hydrogen. Here is your beta hydrogens. Now, if you abstract this hydrogen, it's actually going to result in 1-butene. that's going to be not much stable. But if you're going to abstract this hydrogen here, it puts the double bond between these two carbons, which is going to result in 2-butene. And here is the structure for 2-butene. So in reality, 2-butene is the compound that's formed in major quantity for this reaction. That's because of the presence of large excess of H+. Where the initial alkene that's formed, it's undergoing electrophilic addition reaction. Here is your electrophilic addition reaction. And this is your major product. We already know that the elimination reaction is a stereoselective reaction, wherein the major product that's obtained is the stereoisomer with the largest groups on opposite sides of the double bond, which means a trans compound is formed more excess than the cis isomer, right? So the same thing can be applied in alcohols as well, where the trans product is going to be formed. Now let's find the mechanism for this reaction. So in the first step, the hydroxy group is going to be activated, which means it's going to get converted into a good leaving group. And that's going to be your intermediate. And since this is a secondary alcohol, it's going to go through the E1 mechanism. For the E1 mechanism, we have to draw the carbocation, where this leaving group is going to leave, and it's going to form the secondary carbocation. And here is your secondary carbocation. This secondary carbocation can actually form two different products when a base comes and abstract the beta hydrogens. Now let's identify the alpha hydrogen and beta hydrogens. So here are the two beta carbons, and they have some hydrogens on it. If I'm going to abstract this hydrogen, then it's actually going to result in this as the product. And if I'm going to abstract, let me mark this as B1 and B2. If I'm going to abstract the B2 hydrogen, beta 2 hydrogen, then it's going to result in this product. And obviously we know that this is going to be the minor product and this is going to be the major product because this is going to be highly substituted. And within this major product, there are two different compounds that could be formed. One is your cis isomer, and the other one is going to be a trans isomer. Cis compound, and the other one is going to be a trans compound. So between these two, the trans compound is the one that's formed in major quantity, and we already know that trans compound is the most stable one. We can also conduct the elimination reaction, the dehydration reaction, under mild conditions. Why do we have to use mild conditions? Remember, we are using very strong acids. We are using H2SO4, and that too we are heating it to a certain temperature, which means it can lead to several side products. Right? In order to avoid all these side products and get primarily one product, we wanted to conduct this reaction under mild conditions. So the mild condition is actually going to use phosphorus oxychloride. This is phosphorus oxychloride. And you have to use pyridine, and this reaction needs to be conducted at 0 degrees Celsius. And the product for this reaction is 2-butene. Now let's look into the mechanism for this reaction. Here is a reaction where an E1 dehydration reaction has been converted into an E2 dehydration reaction. Let's see how. This is a secondary alcohol, right? By default, it's going to undergo E1 reaction. But here, it's actually going to be E2 dehydration reaction. Okay, now let's see what's going to happen. Very first step is going to be the activation of the alcohol. Right? We have seen several ways to activate an alcohol, and this is one of the ways to activate an alcohol. Now, the OH, the oxygen with its lone pair of electrons, is going to go attack the electropositive phosphorus, and it's going to thrust the electrons onto chlorine. Let's write the mechanism for this reaction. And now you have an alcohol which is converted into a good leaving group. Or remember, this oxygen still has the hydrogen. And if you want to remove that hydrogen, you have to use pyridine as the base. This pyridine will go and abstract this hydrogen, and now it's been converted into a good leaving group. Okay, now since we are using large excesses of pyridine, the pyridine is actually going to behave as a base to abstract the beta hydrogen. Let's find the beta hydrogens. Here is the alpha carbon, beta carbon, beta carbon. Now you have two hydrogens here on this beta carbon. And again, two hydrogens here. It doesn't really matter which one of these hydrogens you are going to abstract because it's going to result in only one product, right? So when the pyridine goes and abstracts this hydrogen, it pushes these electrons in here and thrusts this leaving group out. So that's going to result in an alkene, cyclohexene in this case. And apart from that, you will also get two molecules of protonated pyridine and your OPOCl2, which is going to be your leaving group. Also, another way to dehydrate an alcohol through the E2 mechanism, and that is by using tosyl chloride. This is sulfonyl chloride. If you want, you can draw the structure for tosyl chloride. It's going to be toluene sulfonyl chloride, which has this structure. And then the first step here again is going to be the oxygen with its lone pair of electrons is going to go attack the sulfur, and the Cl is going to leave, right? And the role of pyridine here again is to abstract the hydrogen on the oxygen, to neutralize the charge on oxygen. The pyridine is going to go grab this hydrogen and thrust the electrons onto oxygen to form a neutral compound. Now this whole thing right here is actually going to be O-tosylate, which can be represented as OTS. Okay, I'm actually going to erase this part and I'm going to replace it with OTS. Okay, now we need to abstract the hydrogen, beta hydrogen. When you react it with a strong base, it's going to go through the E2 mechanism, right? So we need to find the alpha and the beta carbons. So here is your alpha carbon and here are your beta carbons. If any of these two hydrogens are abstracted, it's going to result in the double bond on the first carbon, which is going to look like this. Or if this beta hydrogen has been abstracted, it's going to result in this product. And between these two products, we already know that this is our major product because this is highly substituted.